10.5, solve exponentials and logarithm equations. So in this sessions, we're gonna solve uh, the types of exponential equations and the logarithm equation that we couldn't solve in a 10.2 and 10.3, right? And also we're gonna look at the application problems that using the exponentials and then logarithms. So the first, we're gonna look at logarithm equations. Okay, so logarithm equations we talk about in 10.3 using the definitions, right? Using the definitions of the logarithm to solve. So when can I use the definitions of logarithm? When the logarithms equation is in this form, a single logarithm on one side and a number on the other side. Whenever we can rewrite it into this format, we will always use the definitions because that's the easiest case, because that will allow me to rewrite it into uh, equivalent exponential form and then solve for it. Okay, so that's what we talk about in 10.3. Now, in the next in this sections, what we're gonna do is we're gonna use another property which is very logical. And if you have a logarithm with the same base, and if they are equal, then logically the value of the argument must be equal to each other. So that's one way that we can basically get rid of the logarithms on both sides. So this is when you have multiple logarithms on multiple logarithm terms, okay, on both sides of equations. So right here I put it down the strategy for you, right? So that that way you can analyze the problem and then see this strategy this strategy is pretty much generalized it. Okay, so here's the key things that you need to pay attention. If an equation contains a single number term, okay, a single number term, then basically I can use the definitions. So first thing what we're going to do is we're going to use the properties of logarithms to condense it and then get into one single logarithm on one side and the number on the other side. And then using the definitions of logarithms to rewrite, right? Use the definitions of logarithms to rewrite equivalent exponential equation. And then we're going to solve the equation in step 3 and then check. Because logarithm, you always need to check. If the equations contains, okay, multiple logarithm terms, okay, equation contain multiple logarithm terms. So that means logarithm terms on both sides of equations, and then with no single number term. So that's a key thing, no single number terms. Then what we're gonna do is we're gonna rewrite, okay, equations into a logarithm terms on the left hand side, a logarithm terms on the right hand side using the properties, which is condensing it. Then we're going to use the one-to-one property to say that the argument of the logarithm must be equivalence, and then we solve that. And then finally, the most important thing right here, no matter which case of the logarithm, you always need to check. So let's take a look at on the first example. So first example, I found out that there is a single number term. So that means that right away it sort of give you a hint that I can use the definition, meaning I can rewrite it into equivalent exponential equation form. But first, I have to have a number on one side and then a single logarithm terms on the other side. So therefore, I'm going to try to condense the left-hand side. So using the property from the previous sections, I can say that log of base 3, since this is a subtraction, it must be what? Quotient. So x over first term minus 6. X minus 6, that is equal to 4. So now I have a single logarithms on one side and number on the other side. So I can use the definitions of logarithm, which is rewriting into equivalent exponential form. That is, base to the exponent is equal to the argument. Now we can solve this. 3 to the fourth power is 81 is equal to x over x minus 6. Multiply both sides of equations by the LCD. So in this case, it's 6 minus x minus 6. X minus 6. I multiply both sides. 81, right, times 81 equal to times x over x minus 6. So on the right hand side, x minus 6 cancels out, so I have x is equal to 81x minus, when I distribute it, it will be 486. Solving this, I subtract 81x on both sides, that become negative 80x. And finally, divide both sides by negative 80, which give us a decimal number answer, right? So 486 divided by 80, that gives me 6.075. And finally, we need to check. Where do we check? We check the arguments are positive or not. So if I plug it in right here, okay, if I plug it in right here, 6.075, then it's a positive number. If I plug it in 6.075 right here, it's also a positive number. So therefore, both of my arguments give me a positive argument. So that conclude that this is my answer. Now, next. Again, notice that I have a single number term. So according to the strategy, that tells me I can use the properties of definitions of logarithm. So first, I'm going to try to rewrite a single logarithm on the left-hand side and a number on the right-hand side. So using the property, this allow me to condense it. So that will be log of base 5. Because of this is addition, it will become a product, x times x minus 2 equal to 3. So now I can use the definitions of logarithms to rewrite it into equivalent exponential form. That is, base to the exponent is equal to the argument. That will be 125 is equal to x squared minus 2x. And we are solving quadratic equation, so moving everything to one side. And try to factor. If it is factorable, we are done deal. If it is not factorable, that's where we're going to have to figure out what to use. So 125. And we need to get what? 2 in the middle. So take a moment to think about the factor, see you get the factor or not. So at this point, hopefully you find out that it is not factorable. So we're going to use a quadratic formula. X is equal to minus b plus or minus square root of b squared minus 4 times a times c all over 2a. So this gives us 2 plus or minus square root of 4 plus 500 over 2, which is 2 plus or minus square root of 504 over 2. So 500 4. So take a moment, pause it and take a moment to check, can I simplify the square root of 504 or not? Okay, so 504, this is how we think about it, right? Think about, is there any perfect square number or not? So I'm divided by 4. So 504 divided by 4, that's give me 126. So we know that 4 times 126 is 504. 126 has another perfect square number, that is 9. So 126 divided by 9, that will give me 9 times 14 is 126. So therefore, the largest perfect square number is two perfect square number multiplied together, which is 36. So from here, I can see that 2 plus or minus square root of 36 times 14 divided by 2, which is 2 plus or minus 6 square root of 14 divided by 2. Now finally, to simplify all the way through, I can divide it to both of the terms. Okay? So that gives me 1 plus or minus 3 square root of 14. And that gives us two answers, which is one of them, x is equal to 1 plus 3 square root of 14. That is a positive number, approximately. Okay, so now you have to compute it because we need to check. So you want to have a decimal answer to approximate, see would that work or not, right? So 14, take the square root of 14. Where did my square root sign go? I cannot find my square root. Oh, right here. Okay, square root of 14 and then times with 3 and then you add 1 to it. So I got approximately 12.2249 dot dot dot. And the next one is x is equal to 1 minus 3 square root of 14. 3 times square root of 14. That approximately, this should give me a negative number because 14 the square root and then times 3, that's a negative number, right? And then what? You add 1 to it. So which gives me approximately negative 10.2249 dot dot dot. So clearly when I plug it back into original equations, plug it into x, a negative number, that will not work because remember the argument has to be a positive. So therefore this is not the answer. So my answer will be 1 plus 3 square root of 14. That's the only one. So you have to check. Otherwise it will not work. So now we're going to look at the example that have no single number term in the logarithm equations. Okay, no single number terms in logarithm. So if you look at example 3, I can see that there is no single number term like in the previous example right here and right here, right? So first we're going to try to condense it. So that means I need to rewrite without this factor 2. So according to the property, that factor 2 will become the exponent of the argument. That is equal to log of base 336. According to the property, one-to-one property, if the logarithm with the same base, if they are equal to each other, that means the argument must be equal to each other. So now we are solving this square quadratic equation. So we can use the square root property, which is when you take the square root on both sides, don't forget the plus or minus sign. So this will become x is equal to plus or minus 6. And clearly the negative 6 does not work because when you substitute into here, that will become a negative number, which is wrong, right? According to the concept, the argument cannot be negative. So therefore, my answer will be just 6 after we check in it. So you can see the similarity in the next example, but however, first we're going to have to condense it. So on the left hand side, I'm going to have to make sure it is a single logarithm, and on the right hand side, a single logarithm. So using the property, Since this is a subtractions, I can basically use the quotient rule. So log of base 10 x plus 2 over 4x plus 3, that is equal to log of x to the negative 1 power, because this negative 1 is basically negative 1 power, right? You have to remember it's negative. Now we have this logarithm with both of them is base 10, and if they are equal, now I can say that the argument must be equal to each other. So this is basically, I can rewrite it as x plus 2 over 4x plus 3, 1 over x. So I can use the proportion idea type of equations to solve this, which is cross multiply. And at the same time, you need to remember the restrictions from here. Okay, from here, I know that x cannot be equal to 0. X cannot be equal to this denominator become 0. So it will be what? Negative 3 over 4 when you solve it. So finally, if I cross multiply, that will be x times x plus 2, and then 1 times 4x plus 3. So distributing it, it will become x squared plus 2x is equal to 4x plus 3. We are solving for quadratic equations, so that means I'm going to have to move everything to one side. So subtracting 4x on both sides, subtracting 3 on both sides, which allow us to factor, which is minus 3x plus 1 equal to 0. According to the zero factor property, I can say that x minus 3 is equal to 0, x plus 1 is equal to 0. So I have two possible solutions. X is equal to 3 or negative 1. And clearly negative 1 doesn't work, because if I plug it into here, my argument is a negative value, so therefore it doesn't work. If 1 doesn't work, you don't need to check the other ones. So definitely this one is out. If I plug it in 3, this right here, that will be positive. If I plug it in 3 right here, that will be positive, and also right here is positive. So therefore my only answer is 3. And so now in the next video, we're going to look at the exponential equations.